This reaction is known as the Friedel Crafts Alkylation reaction. It's where you alkylate a benzene. And it's a type of electrophilic aromatic substitution reaction. And so the first step in this, so we have our iron tribromide here. Now sometimes you'll see aluminum trichloride as well. There's a chlorine here. But essentially it's a benzene ring, an alkyl halide, and then you have some metal trihalide that is a Lewis acid catalyst. So the first step is that our halide attacks our Lewis acid, and we form a complex like this, where the bromine, or the halide, the bromine in this case, is bound to kind of both at the same time. And so it has a positive charge on there. We have a negative charge on our iron with its three other bromines. And because bromine doesn't like that, essentially what it is, all right, we're going to give those electrons to bromine, and we're going to form a carbocation intermediate like this. Now, if you know anything about carbocations, you should know that primary carbocations are very unstable. So while this reaction mechanism is generally taught as carbocation, know that in reality, this primary carbocation likely isn't forming. And so what it might be taught to you as is there is kind of like a partial positive here, because this bromine's pulling some electron density. There's not like a true formal positive charge. There is, but so, and then this is what's get attacked. It's not a true carbocation. Remember, as always, you know your professor, not me, so go with what they want. But what I find the easiest to understand for students, if we just go with a straight carbocation mechanism, even if primary carbocation likely wouldn't form. So the next thing that happens is our ring comes and attacks that carbocation. Or if we're not going with the carbocation, we're using the partial positive, it would come and attack our partial positive there. And then we would give those electrons to bromine. We break that bond then. Now, we have an intermediate here, because we just broke up that aromaticity. We have our new group here as a proton. Now we have another carbocation right here. And we have, what do we have? We have our iron, I guess tetrabromide now, and it has a negative charge. And so what's going to happen is that bromine that we gave up originally, well, I don't know if it's the actual same one, there's 4 bromines here because there's a negative charge on our iron, is going to come and steal this proton, or abstract the proton is the correct speak, and we're going to give those electrons back and rearomatize. We're going to regenerate the aromaticity. We're going to make our product right there. That's the basic mechanism. There are 3 things you need to know about this. First off, we talked about this carbocation mechanism, how it's taught. Now let's think about this for a second. I'm going to erase this here. So, what do we know about carbocations? Is that they will always try to move to a place that is more stable for them. So say this was the halide we started with, and we form our carbocation. What do we know about carbocations? We already said they're very unstable, and we know that they're going to move. So what's going to happen? We're going to have a hydride shift. So actually this is going to be our carbocation, and this is what gets attacked by the ring. So if we did this, we're not going to get this. That won't form. Instead, we're going to get this, where we have isopropylbenzene. We won't get N-propylbenzene. We'll get isopropylbenzene. So it is susceptible to carbocation rearrangement. Secondly, we'll talk about directing groups in another video. But directing groups determine where the incoming electrophile or incoming group will go on the ring. And alkyl groups like this are what's known as weakly activating or weakly electron donating. So not only do we have our nice product here, but now it's actually more reactive than our starting material. So it's hard to control this at just one alkylation. And secondly, if we have an extremely electron withdrawing group, like say a nitro group on there, it becomes very difficult to alkylate it. But that's okay. So those are three big restrictions. And now, if you want to know how you can get this, there's something called Friedel Crafts acylation, and then you can use a reduction to reduce it down to get this, and we'll talk about that in the Friedel Crafts acylation video.